When the base current is equal to 0, the operating point is here. At this point, VCE is approximately equal to VCC, and the collector current is approximately equal to 0. When the Q point lies anywhere on this green line of IB being equal to 0, the transistor must be operating in the cutoff region. The table on the left lists down all these key points. The equation VCE is derived by applying Kirchhoff's voltage law on the collector-emitter biasing circuit that has been discussed in BJT Part 1. This equation holds for all regions of operation. Look at here. The base current is equal to 0. Therefore, the circuit is biased in the cutoff region. The collector current is approximately equal to 0, and VCE is approximately equal to VCC. If we ignore the very small collector to emitter leakage current ICO, then IC is equal to 0, and VCE is equal to VCC. Referring to this current and voltage values, we can conclude that the transistor operates as an open switch. Let's explain the reasons for this now. With the switch being opened, the current must be 0. Because of Ohm's law, V equal to IR, when the current is 0, the voltage difference across the resistor must be 0 too. So by Kirchhoff voltage law, the voltage difference across the switch must be equal to VCC. Now let's compare these two circuits. Both the transistor and the open switch have 0 current. The voltage difference across them are both equal to the supply voltage VCC. Therefore, the transistor operates as an open switch when it is biased in the cutoff region. When IB is 0, IC is 0. When IB is equal to 50 microamperes, IC is equal to 10 milliamperes. When IB is equal to 100 microamperes, IC is equal to 20 milliamperes, and so on. From this data, we can see that IC is proportional to IB. The proportionality constant is called DC current gain. It can be labeled as beta DC, beta, or HFE. The label HFE is commonly used in the transistor datasheets. Beta can be in the range of less than 20 to a few hundreds. When the Q point is in the active region, the value of VCE must be larger than VCE saturation and smaller than VCC. In theoretical discussions, VCE saturation is normally given as either 0.2 volt or 0.3 volt. If you look at the active region carefully, you'll find that it does not cover the horizontal line of IB being equal to 0. It also does not cover this vertical line above the value of VCE saturation. Let's see the reason for that. If the Q point lies on this horizontal line, the transistor must be operating in the cutoff region instead of the active region. And if the Q point lies on this vertical line, the transistor must be operating in the saturation region instead. Let's look at this summary table. When the transistor is biased in the active or linear region, IC is equal to beta multiplies IB. VCE is larger than VCE saturation, but smaller than VCC. These three equations have already been discussed in BJT Part 1. As we often need to apply them in this unit, they are listed here to refresh your memory. When a transistor operates in the active region, IC is equal to beta multiplies IB. When IB increases, IC increases proportionally. Therefore, The transistor operates as a current amplifier when it is biased in the active region.